Hello everyone, it's fantastic to be here with you today at the AWS Health and Life Science Day. My name is Dr. Denis Bauer. I'm a research scientist, professor at an Australian university and AWS hero. Today, I want to talk to you about cloud-based bioinformatics, or how to scale machine learning to uncover the genome's role in complex diseases. By the end of this talk, I hope that I've convinced you that in the era of mega biobanks, we need to rethink how we analyze the data. The data is just too big and too complex to be moved around. Therefore, the analysis needs to go to the data. But before we go there, allow me to introduce the research organization that I am part of, which is Australia's government research agency, CSIRO. At CSIRO, we're really passionate about translating research into products that people can use in their everyday lives. Our most famous product is Wi-Fi, which CSIRO invented together with Macquarie University, which is now used in more than 5 billion devices worldwide. On the digital side, the Australian eHealth Research Centre has developed the first clinically validated mobile app for heart attack rehabilitation. And on a lighter note, CSIRO has invented the Total Wellbeing Diet, which is now on the book bestseller list, alongside Harry Potter and the Da Vinci Code. From that perspective, we do have a nice balance between products that people enjoy and products that people need. Today, I want to talk to you about cloud-based bioinformatics in 3 parts. Tell you 3 stories. The first one is around how to scale to population-scale datasets. The second one is around data interoperability and how to bring the insights from those large datasets into the clinical system. And the last one is around science accessibility, how the academic development in algorithms and analysis workflows can be used in the industry settings in order to empower and accelerate innovation. The genomic analysis, as I see it today, has 2 problems. The first one is that the cohort sizes are getting larger and larger. And the second one is that the diseases that the healthcare system truly cares about are complex, multigenic diseases. Therefore, bringing in the interactions between genes is absolutely crucial, and current analysis technologies can typically not handle that. Now, the first problem can be addressed by throwing more compute at it. But there's a limitation to that. And what I would argue is that we truly need to embrace big data technology in order to solve the problems that we have at hand. To illustrate that, I've put together a table which showcases how high-performance compute is really geared towards compute-intensive tasks. And this is because the node system in there, so the individual compute nodes, have CPUs on them, multiple CPUs on them, fair enough. But the boundaries between multiple nodes is solid. In order to bridge that boundary and use more CPUs in the analysis that you're doing, you do need to implement something bespoke. In the fast-moving genomic space, this bespoke analysis is a real bottleneck. Therefore, using more native big data technologies is the solution that we went for. We're using Apache Spark. And Apache Spark has the benefit that it is truly geared towards data-intensive tasks. And this is because the node boundaries is dissolved, meaning that the cluster, the Apache Spark cluster, has basically access to every CPU in that entity. For that, we have developed VariantSpark, which uses Apache Spark in order to accelerate the analysis that we want to do. VariantSpark is a machine learning library specifically designed for analyzing genomic data. It scales with dataset size increases linearly compared to other solutions that scale exponentially. VariantSpark is hence 3.6 times faster on today's data and scale to tomorrow's data, 1 trillion data points, with analyzing it in 15 hours, whereas other technology that scale exponentially would take 100,000 years to compute. VariantSpark uses the AWS MapReduce cluster in its core. It brings in data directly from S3, encrypted data, that only gets decrypted on the individual compute nodes using the Key Management System, KMS. Now we're bringing this setup to Project MINE, which is one of the largest genomic consortia in the world, looking at the molecular origin of the motor neuron disease that Stephen Hawking suffered from, ALS. VariantSpark is applied to a case control study of 22,000 whole genome sequencing datasets to identify the genes that are driving the disease and ultimately finding better treatments. This brings me to the second story around interoperable data exchange. Now, in order to bring these large cohort datasets to the world, we do need to apply a more scalable solution to that. And I would argue that cloud technology is the way to do that. Specifically, serverless technology. Now, if you're not familiar with serverless, allow me to walk you through how I think about serverless. Now, we're all familiar with desktop compute. The way I think about that is like having full control over everything that you install in there. You have the full flexibility. It is cost effective. But there's an overhead to that. You have to look after the system and it is not scalable. It is akin of having your own car. You only have that one car and you need to bring it to service. It will be much easier if you had a chauffeur. With that chauffeur, he can take the car to the service and drive you around, which is akin to cloud services or cloud servers, especially in auto-scaling group. This allows you the flexibility of scaling up and down to the solutions or to the tasks that you have at hand. There's no overhead because the public cloud providers care for the individual servers. And it is certainly scalable, but it is not necessarily cost effective. Like a chauffeur, having an auto-scaling group, it does not just go away simply or easily. And therefore you're paying this little bit of extra overhead in order to have that flexibility. And this is exactly where serverless comes in. With serverless, you do have the agility, you do have the flexibility, there's no overhead and the scalability, but you don't have the cost because the infrastructure costs nothing if you're not actually using it. And I think of this like a ride-sharing app where you can demand a specific car at the point in time and then it goes away without any cost. Bringing this flexibility into genomic data exchange, we have developed Serverless Beacon, a cloud-native data exchange protocol. So it is redeveloping the traditional Beacon protocol, which is now one of the accepted data exchange protocols around the world. But unlike the traditional Beacon, Serverless Beacon does not require the data to be consolidated into one massive database. This truly allows the scalability to large-scale datasets, population-scale datasets, for example, where you could deal with 30 quadrillion data points. That is 300,000 samples times 100,000 variants each. In order to handle those kinds of datasets, you do need to have parallelization in there, and Serverless Beacon allows for that. It also allows the handling of dynamic patient consent. Because the data does not need to be in one database, you can easily take away individual files depending on the patient's wishes, without the whole system falling over or having to be recomputed. This flexibility also allows for more real-time analysis. So rather than just going in and saying, have you seen a particular genotype at a particular location, and the system saying yes, no, or coming back with a frequency, you could analyze the data on the fly, creating histograms, comparing it to other data sets. And this truly opens up the whole space to interactive data analysis using data exchange protocols. Serverless Beacon is built on AWS Lambda, and in fact uses a lot of other things from the serverless ecosystem like DynamoDB or the SNS topic. What I'm showing here is the data ingestion engine that registers individual files as they come on board. What makes this architecture unique is that we are able to split the individual files based on their sizes using recursion. This allows to partition the individual tasks so that the overall analysis time can stay the same, irrespective of what kind of dataset size you're handling. The query engine is much simpler. It is also based on AWS Lambda, but it does not require a recursion. Being able to parallelize that way is a massive cost saving. In fact, it's a 300-fold cost saving per month. So rather than paying $4,000 per month, Serverless Beacon allows you to set up a system like that with just $15 a month. So for less than a cup of coffee per day, you can contribute the genomic dataset that you have to the world. Being able to overlay this genomic data with health data, other medical data, would truly advance the field substantially. But this is currently held back by the medical data not being accessible. For that, CSIRO has developed the Ontoserver, a one-stop shop for advanced terminology use. The Ontoserver is built on FHIR and enables syndication across clinical terminologies. It supports the advanced use of SNOMED-CT and underpins UK's national health system. In fact, it has 75 licensees globally and truly builds a whole universe around interoperable data exchange using terminologies. This brings me to the last story around science accessibility and how the industry can benefit from the solutions that are developed in the academic space. In my mind, cloud really helps with that journey. It makes talent and solutions so much more accessible. Individual bespoke solutions that are developed on one side of the world can easily be rolled out on the other without latency and within the cloud account of the people that want it. This really bridges the gap between research and industry. To accelerate that, we have put VariantSpark on the AWS Marketplace. It is the first digital product, health product, from a public sector organization worldwide to do so. And this truly enables reproducible research because not only is the algorithm VariantSpark in there, but also this whole architecture, the best practice workflows, so that people that get started can start it the right way. This marketplace offering of VariantSpark is security hardened through AWS, meaning that it follows the latest security standards that AWS recommends. This truly allows reproducible research because everything is included in this package, from the algorithm, the architecture, the security features, and the data exchange information in there. It's all bundled up in one infrastructure as code element that can be deployed to the user's account and can be spun up there automatically. Being able to build on someone else's solution this easily really fosters global collaborations and build systems that are larger than the sum of their parts. The three things to remember from my talk are that in the era of mega biobanks, we need to get comfortable with analyzing really large-scale datasets. And for that, we have developed VariantSpark, which is a machine learning library specifically designed for whole genome population-scale datasets. It allows association studies to be conducted that take gene-gene interactions into account to truly analyze data and diseases that are of value to the healthcare system. The second point is that we need to exchange data globally. And for that, we have developed Serverless Beacon, which is 99% cheaper than the current implementation of Beacon and allows dynamic patient consent to be handled more natively because it does not require the data to be consolidated into a single database. So individual files can be taken out at any moment in time without the whole system falling over or having to be recomputed. Being so cheap and easy to maintain hopefully inspires more organizations around the world to share their data and contribute to genetic research. Now, in order to bring genomic data into the healthcare system, we have developed the Ontoserver, which is a one-stop shop for clinical terminology and therefore bringing in the genomic data into the healthcare system. And the most important point from my talk is that we need to bring the analytics to the data. And in my mind, the AWS Marketplace is the perfect vehicle for that, because it allows reproducible research by bringing the analysis, the algorithm, the workflow, the architecture directly to the user and next to their data. And this truly will enable us to build solutions that are larger than the sum of their parts. With that, thank you very much for listening. And if you're interested in other solutions that we have developed, please visit our webpage. See you soon.